We establish trial aggregate blends by combining our aggregate sources in different proportions to meet superpave gradation specifications. For trial blend 1, we'll be using 45% of the number 78 aggregate, 22% of the wash screenings, and 33% of the dry screenings. These mass proportions were combined with the gradation information from the different aggregates using the equation on this slide to arrive at the gradation in the table. This is the same equation that we followed in the aggregate portion of this class when we covered aggregate gradation blending. We give superpave asphalt mixtures a designation based on their nominal maximum aggregate size, abbreviated NMAS. The nominal maximum aggregate size is defined as one sieve size larger than the first sieve to retain more than 10% of the aggregate. Here is our gradation information for trial blend 1. If we look at the information given here, we see that we're given percent passing instead of percent retained. Anything that passes is not retained. Therefore, percent retained is simply 100 minus the percent passing. If we look at the gradation data here, we see that the 4.75 millimeter sieve is the first to retain more than 10% of the aggregate. It retains 29%. If we go to one sieve size larger, we see that our nominal maximum aggregate size is 9.5 millimeters. Please keep in mind that we give the designation based on millimeters and not inches. The graph on this slide shows our percent passing versus our sieve size raised to the 0.45 power. We see our three gradation curves plotted along with the superpave specifications. Superpave gradation specifications include control points, which are points where the gradation must pass through, denoted by the X's on the graph, and a restricted zone, which the gradation curves must fall outside of. We see that all three of our gradations meet the superpave specification, and we see that trial blend 1 falls the lowest and trial blend 3 falls the highest on this scale. This indicates that trial blend 1 is the coarsest and trial blend 3 is the finest. Superpave asphalt mixture design is based on volumetric properties. Understanding volumetric properties requires knowing the relationship between masses and volumes in our materials, which is designated based on our specific gravities. When we talk about aggregates in terms of asphalt mixture design, we're concerned with three specific gravity quantities. These include the bulk specific gravity, apparent specific gravity, and effective specific gravity. When we look at an aggregate particle within an asphalt mixture, we'll see that we have solid volume, which is the aggregate itself, and there will be pores. Asphalt binder is a viscous fluid. Therefore, it cannot penetrate all the way into aggregate pores. Rather, it will get trapped at some depth. Therefore, when we discuss aggregate pores, we divide the volume into asphalt impermeable voids and absorbed asphalt quantities. When we consider the bulk-specific gravity, we divide the mass of the aggregate by the bulk volume, which includes the solid, impermeable void volume, and absorbed asphalt volume. Apparent specific gravity, on the other hand, only considers the solid aggregate volume. Therefore, the apparent specific gravity should always exceed the bulk specific gravity value. Lastly, in asphalt mixtures, we consider the effective specific gravity, which is the mass of the aggregate divided by the sum of the solid volume and impermeable asphalt void volumes times the density of water. After establishing our trial aggregate blends, we have to calculate the blended bulk and apparent specific gravities. We typically only measure the specific gravities of our individual aggregate sources, and then we apply equations to determine the blended specific gravity properties. Equation 1 shows how you can calculate the blended bulk specific gravity as a function of your individual mass percentages of your different aggregate sources and your individual bulk specific gravities. We will solve equation 1 for trial blend 1. Here's our information for trial blend 1. We see that we have P1 is equal to 45 for the number 78, P2 is 22, and P3 is 33. In the denominator, we take our individual mass percentages and divide by the respective specific gravities. For the number 78, the specific gravity is 2.546. For our wash screenings, it's 2.582. And for the dry screenings, it is 2.56. This leads to a blended bulk specific gravity of 2.558. Equation 2 is used to calculate the apparent specific gravity of our aggregate blend. You'll see that equation 2 appears identical to equation 1, except for wherever bulk specific gravity appeared in equation 1, we see apparent specific gravity in equation 2. We'll solve for the apparent specific gravity of trial blend 1. The information for trial blend 1 is given in the table. We see that our percentages, P1, P2, and P3 remain the same. And our apparent specific gravities differ from our bulk. So we see that for our first aggregate source, we take the mass fraction, 45%, and divide by 2.639, the apparent specific gravity of the number 78. And then we take 22%, the amount of wash screenings we're using, and divide by 2.631, its specific gravity. And then we take 33%, which corresponds to our dry screening, and divide by its specific gravity of 2.621. This gives us a blended bulk apparent specific gravity of 2.631. Determining the effective specific gravity of aggregates requires knowledge of how binder absorbs into the aggregate particles. This is a function of both the asphalt binder you're using and your aggregates. Therefore, at this stage in the mix design process, we simply estimate our effective specific gravity based on our apparent and bulk specific gravities for our aggregate blend. For our example, we calculated that our bulk specific gravity was 2.558 and our apparent is 2.631. Therefore, our estimated effective specific gravity is 2.616.